Okay, let's begin. Now we'll start with the consequences of partial derivatives. So we start from here. This is the definition of partial derivatives. We know the techniques of taking derivatives of one variable. So if there are several variables, we use the same technique. If you are taking derivative with respect to x, everything else is fixed. So you just take the derivative with respect to x. So what is the picture of this? Let's look at the picture. Now we have a function of two variables. So the domain is this. The function takes all these numbers and gives you a number. So for each number, it gives you a height. So there is a surface here. Okay, so the whole game is played in R3. So we start with the drawing coordinates for R3. Okay, so we have something like this. So of course, the nice thing is in the first octant, we can see this part easily. Okay, so everything is taking place around the point x sub 0, y sub 0. Okay, so suppose f x y is a nice function defined in a neighborhood, in some neighborhood of x sub 0, y sub 0. Okay? So what does nice? Nice means that every time we think of a function, it has a nice graph, it has a surface over there, there are no breaks in it. Okay, so the first thing that comes to mind. Later on, we'll make a technical definition of nice. So we'll look at this thing. If this is nice, so what are the technical conditions that always describe things like this? So the first thing is, the first thing is we'll look at the graph of this. So suppose the graph is something like this. Okay, so this is the graph of z equals f of x, y. So any point here, a typical point here is of the form x, y, f of x, y. Okay. So now we try to understand what happens on top of this. So you see we are examining things here. So we look at, say, like this, suppose here. So this is the point. This is the point x sub 0, y sub 0, f of x sub 0, y sub 0. Okay. Now what did we do? We restricted the function to this. So y sub 0 was fixed. So let me find the same color here. So first we did this one. Okay. So we restricted the function here. A typical point was x, y sub 0. Okay. Now when you restrict the function there, you look at the part in the graph. The graph is something like this. Okay. So you have this part in the graph. Okay. And then we do the other one. We restrict it to like this, to this line. So a typical point here is x sub 0, y. And corresponding to that, we have this. Okay. So, well, I think that much color is enough. Okay, so you restrict the function here. You have a function of a single variable. Now let's look at this. Let's look at the red one first of all. It's easier to see. So forget about everything. Just consider this plane. Suppose we have a plane like this, an imaginary plane like this. Okay. Just don't see anything except the red ones. We have a function and we have a graph here. And at this point, that graph has a derivative. We are assuming that the derivatives exist. So it has a tangent line. The tangent line has that slope. Okay, so let's draw the tangent line. Okay, so here we have this thing. This is now the tangent line to this red curve. Okay, its slope its slope at that point is the derivative that we calculated along the red line. What is this? X sub 0 is fixed. So it's the derivative with respect to y. Okay? We are moving along y. Okay, so there's nothing to memorize here. We are moving along y, so the slope tells us the derivative with respect to y. Okay, so its derivative, its slope is derivative of f with respect to y at the point x sub 0, y sub 0, because only y is moving. Okay, now we have again the same thing here. We have a tangent line here like this. Okay, so this is the tangent line. So this one is now the tangent line to the purple curve. So you do the same thing, but now it is a little complicated. You only see the purple things. So you have a purple plane. You cut everything with this purple plane. And then along this direction, you have this curve. It has a tangent line at that point, and its slope is derivative of f with respect to x at the point x sub 0, y sub 0. Okay, so what makes this thing nice is that I can move this point around, and I will have all these pictures again. Okay, so I will try to make this in terms of, we will try to explain it in terms of the derivative. Okay, so the whole philosophy of calculus is that you have a function. If it is differentiable, by looking at the derivatives, we want to say something about the curve. Okay, so here we have that the derivatives exist at that point. What can it say about the function? Okay, so before that, okay, so let me first of all give an example where the derivatives exist nicely, but you see the function is not nice. We haven't defined the word nice yet, but obviously we all have, when we see a function, everybody will agree that it's a nice surface. Now I'll give you another surface, and everybody will agree that you don't want to see it again. Okay. So, but, a big but, the existence of partial derivatives at a point does not say much about the function. Okay, so here's an example. Consider the function f of x, y. So this is equal to, let's say, 1 if x, y equals 0. So this is either one of them is 0. If one of them is 0, y is free. So we are moving along the y-axis. Or this one is 0. We are moving along the x-axis. So this means along the x or y-axis. So the function takes the value 1 along these things, and everywhere else it is 0 otherwise. So let's look at the graph of this function. The graph of this function is only, let us look at it in the first octant. Okay, so the function is, okay, let's do it red so to exaggerate. Along the x-axis it is equal to 1, and also it goes like this. So since I'll need derivatives, let me extend this a little bit to these sides. Okay, so it goes like this. And along y-axis it is again 1, so it is like this. And everywhere else the function, this is the graph of the function. The function is 0, okay? Except that here it doesn't take 0. As you are moving here, the function suddenly jumps here, okay? So you see this function is not continuous along the x and y axis. In particular, the function is not continuous at the origin. But look at this interpretation. The derivatives must exist there, okay? Because in order to see the derivative with respect to y, I just cut it with a plane parallel to z-axis, but along the direction of y, okay? So if you just look at this thing, forget about the x-axis because now x sub 0, y sub 0 is the origin. So we are not moving things around. Everything is here. Forget about the x-axis. In the yz plane, I have this red curve. Obviously, it is differentiable. It has a tangent. Its tangent is equal to itself. The slope is 0. And similarly here. Let's see if algebraically we also get the same picture. Okay, so first observe that f is not continuous at the origin. It is not continuous at these points also, but now we are just looking at the origin. However, derivative of f with respect to x at 0, 0 is equal to limit x goes to 0. Okay, x goes to 0, derivative of x 0 minus f 0, 0 divided by x. Okay, so this is limit x goes to 0. Well, what is this value? This times this is 0, so it is 1. Minus this times this is 0, so it is 1 divided by x. So this is, you look at this thing, this is 0 over x. X is different than 0, so this is 0. So this is limit x goes to 0 of 0. So this is 0. This is the slope of the tangent line at this point. Well, that's as expected. The line is parallel to y-axis here, so its slope is 0. And similarly, derivative of, so let me just say similarly. Derivative of f respect to y, well, this one I calculated the derivative in this direction. Now this one calculates the derivative in this direction. 0, 0 is 0. So you see partial derivatives exist, but the function is not continuous. So this is the first place where we start suspecting that derivative story of several variables is going to be slightly different than the theory of one variable, because in one variable, if the derivative exists, the function is continuous. Okay, so we immediately know that, and the proof of that is easy. Okay, so the existence of, let me write this here. So the existence of partial derivatives at a point does not guarantee continuity at that point. Okay, I do this slowly because the theory is going to be different here. Okay, so what is the difference between this and this? We want to call this nice. We want to call this not so nice at the origin. At the origin, well, at this point, you see that there is a tangent plane here. Okay, so these two lines, these two green tangent lines generate a plane here, and that plane is tangent to the surface here, and it approximates the surface quite nicely because tangent lines approximate the curve nicely. Here you don't have a tangent plane here. If you insist that these two lines will generate a plane, and if we can say let's arrange our definition of tangent plane so that these two red lines will give a plane, and we'll call it the tangent plane at that point, but it has nothing to do with the function. If you move slightly away from the origin, the function is 0. Ne oldu, Stewart öbür dünyadan mesaj mı gönderdi? That wasn't what I wrote in my book, he says. Okay, so you see the tangent line does not approximate the function around here because the idea is you can write the equation of the tangent line very easily. It's a linear expression at that point. And then if you move slightly away from that point, you can easily calculate the tangent, the value on the tangent line that approximates the actual value of the surface. The difference will be small. But here it's not the case. The difference is, as soon as you move a little bit, the difference is 1. So if you choose an epsilon as your precision less than 1, it's not working. Okay, so it's the existence of tangent planes at that point which will make a function nice. Okay, so we'll again go step by step and make it more precise. Okay, so it says here, let's see, I don't want to miss anything here. Okay, so the next thing is in this section, just to look at higher derivatives. Why don't I pass to what I'm trying to do? Well, tangent planes and linear approximations is next section, but okay, so let me first, before I finish this technical description of nice, let me finish this section with the the technicalities of higher derivatives. Okay, so let's go one more thing here. Okay, so let me mention this. So we want the existence of a tangent plane at a point for the function to be nice at that point. Okay, here tangent plane, so this is a linear expression algebraically, or a plane geometrically, which approximates the function around that point. The approximation, we are not interested that much in actually getting numbers as approximation, but approximating, if we force a function to be approximated by a linear function, so if we force the surface to be approximated by the tangent plane, this imposes a nice condition on the function, on the surface, on the function which gives the surface, okay? So it forces the function to behave. Why do we want functions to behave? Because we have certain expectations when we are doing calculations, and if a function is going wild, we will not do calculations with that function, at least with these rules. We have certain rules, and those rules apply to certain nice functions. So the idea is to recognize which those functions are nice so that we can nicely and sometimes blindly apply our techniques. Okay? So before we come to, to this one, okay? So before that, some technicalities. So notice that partial derivative of f respect to x evaluated at an arbitrary point is also a function. Also a function of x, y, and we can talk about its partial derivatives. Okay, so partial derivative of this thing with respect to x, partial derivative with respect to x. So these are notation now. You are saying that you are taking derivative twice, and you are taking derivative of x twice. What if I take the derivative with respect to y of this, partial derivative of this? Okay, so this is partial derivative of f with respect to. Now, what is the order? First, I take the derivative with respect to x, partial derivative x, y. Then I take x. Okay. Okay. So the operator is first I hit with x, then I hit with y. So the notation here is the fxx. The notation here is the reverse of this, because here, when I'm doing this, I'm talking about the order here, okay? But here, this one says that I take the derivative. When I do this, okay, so you read this as fx. I have a function, I'm taking its derivative. So I have a function of x, I'm taking its derivative with respect to y. So if you think about it this way, the ordering is easy. Okay, so this is derivative xy. And obviously there is also here the other one. So we also have derivative yx. Okay, so this is the partial derivative with respect to x of partial derivative with respect to y. Okay, so when are these two things equal? When are they equal? When you do this with polynomials, you will find out that they are always the same. Okay? When you do it with rational functions, they are going to be the same if you do it at a point where the denominator is not 0. Sometimes if you do it even at a point where the denominator is 0 and the limit exists, so the function has a value there, sometimes they will be equal, sometimes they will not be. Okay, so you catch a situation where these partial derivatives are not the same. So you say, since I haven't tried all the function, there may be many wild functions for which the partial derivatives may not exist. So how do I know that these partial derivatives, these are called mixed partial derivatives? How do I know that they will be equal? So what is the use of this in everyday life? Well, when I'm talking about in everyday life, I'm talking about our everyday life. You keep taking derivatives. Okay. Sometimes if you take the derivative with respect to x first, a lot of things will be killed. You'll get a simple function, and then you take the derivative with respect to y. But before you do that, okay, so if you do it this way, if you first take the derivative with respect to x, a lot of things will be killed, okay? And then you have an easy function to take the derivative y. But if you do it this way, derivative with respect to y is very complicated, okay? And then you take it, and then you have to take x, okay? You have to, if you knew that they were the same, if there's an easy way to check that they are going to be the same, obviously you choose that. Okay, so for example, suppose the function has, let me continue with this one. For example, suppose the function has a complicated function in y with no expression of x in it, plus something with x. Okay, now if you take the derivative of this with respect to y first, okay, so you'll take the derivative of this complicated function with respect to y, and in the next stage, when you are taking the derivative with respect to x, all of this is killed because there's no x in it. Okay, if you could do it the other way around, you would kill it before taking derivatives. Okay, so this is your everyday life. So that's why we want to know when these two things are the same. Fortunately, there is a nice way to check that. I'll write the theorem. The name of this theorem changes every 3 or 4 years. So this year, I think it is called the Claros theorem. So it is clear that Clara did this, but there are other people who also did. So let me check, maybe I wrote his name correctly. Okay, so last year or the year before, it was Euler's theorem. At some time, it was called Schwarz theorem. Okay, so I didn't call it Sartre's theorem yet, but it changes every year. It says that, okay, so if f is defined around x sub 0, y sub 0, and fxy, fyz are continuous. I think if they are continuous at x sub 0, it is sufficient, but let's say around x sub 0, y sub 0, then the mixed partials are the same, f, y, z. Okay? So it depends on how you are proving these things. So let me check what the book says. Well, in Stewart's version, Stewart wants these things to be continuous around this, but in most cases, if you find a careful proof, continuity at that point should suffice. But with most of the functions we are dealing with, you stare at these functions and you know they are continuous. So, for example, with polynomials, you go back to your examples. You never discover such theorems if you don't do childish calculations on your own, try lots of crazy things. Okay? If you don't do that, you never discover anything. So you have lots of examples. From them, you come up with the conclusion, and the conclusion is that if the mixed partials are continuous, then they are going to be the same. It doesn't matter in which way you are doing this. So for example, go back to polynomials. With polynomials, you can take the derivative in any way you like. You'll always get the same result. Why? Because when you take the derivatives of polynomials, you get polynomials, and polynomials are continuous everywhere. Okay? So that's why there you have the same thing. With rational functions, if you take the derivatives of rational functions at a point where it is defined, where the denominator is not 0, you get another rational function with the same denominator squared. Okay, so again, it is defined there. So everything is continuous. So again, with rational functions, it works. But we have a bad example. So I think I have an example here. I'll do that example in a minute. So why don't I do it now? Because we can do the rest later. So here is an example where the mixed partial derivatives are not the same. So we have to find a function. Yes? Z nereden? Z is x. Okay. So that's not a question, that's a correction. You say it should be x, y. Burada da z yazmışım değil mi? X, y, x. Okay. Since you don't say anything, I write whatever I like. So if it is wrong, I'll blame you because I said I'm checking if the class is sleeping, and I find out that the class is sleeping, but somebody woke up. Okay, so that's now in order to find an example where these partial derivatives exist but are not equal, we have to find a function. So it must be that after I take the derivative twice, the function will not be continuous at that point. Okay, so easiest way is to think about a rational function where the denominator vanishes. Okay, so if you take their antiderivatives, you will again have, when you start with f will be a rational function where the denominator vanishes, but we have to choose this rational function such that the limits exist so that the function is defined there. Okay, so I can take derivatives, because when you are taking derivative at a point, you need the value of the point, value of the function at that point. Okay, so that's why we have this strange looking function, if I can find it here. So this is an exercise in the book. Okay, so example of a function f for which f x y at 0, 0 is different than f y x at 0, 0. So this time I didn't write set. Okay, so this is an exercise from the book. It's exercise 105 on page 967. So page 967, exercise 105. So the function is this. So as you expect, we are going to write a rational function whose limits at the origin exist. But as you keep taking derivatives, the limit will not exist. Okay? If the limit does not exist, then the function is not continuous there. So how can you do this? When you take the limit, the numerator will become smaller. Okay, then the denominator will increase. So let's check. Okay, so this is a typical example. Somebody found this example, and everybody uses this because if one bad example exists, you can construct others. So everyone is convinced about this. Okay, so you see that the limit of this exists as x, y go to 0 because it is the sum of two terms. In this term, you see that 3 over 2 plus 1 over 2 is already larger than 1, so the limit exists and 0. For the other one, again, 1 over 2 plus 3 over 2 larger than 1, limit exists. So we have the sum of two objects, two functions whose limit at the origin exists and is 0. So the limit at the origin is 0. X, y is equal to 0, 0. Okay? So this is a continuous function. Check that f is continuous on R2. Obviously, this part doesn't have anything. The denominator does not vanish anywhere else, so it's a rational function, continuous, differentiable. All mixed partial derivatives exist. Okay? If you are calculating the partial derivatives at any point other than the origin, you keep playing with this thing. You get a rational function whose denominator is x squared plus y squared raised to some power. So it doesn't vanish. You get a nice continuous function. So all mixed partial derivatives are continuous and are equal to each other. Well, in this sense, okay, at a point other than the origin. So what we'll check is what happens at the origin. Okay. So we check, first of all, the derivative with respect to x at the origin. So I'll just do this one, and the others I'll just write the answers. Okay. For this one, okay, so this is limit delta x goes to 0, f of delta x 0 minus f of 0, 0 divided by delta x. Okay. So if y is equal to 0, you see that the numerator is 0. Limit delta x goes to 0. So this is 0 minus the value of the function at 0, 0 is here 0 divided by something non-zero. So this is limit delta x goes to 0 of 0 is 0. Okay. So similarly, fy 0, 0 is 0. Okay. Now I did these calculations, but okay. So we also have to check that now the these things are continuous at the origin, but maybe we don't. Okay, let me look at this one. Okay, so check just to understand what's happening. Limit x, y goes to 0, 0 of fx xy. So if xy is going to 0, 0, xy is not the origin. So we are talking about this function. Okay, so you take the derivative of this and you put it here. Okay, so just for one case, let me write this. So you take the derivative of this. Okay, so x 5 minus 4 x cubed y cubed minus x y 4 divided by x squared plus y squared squared. You check that this limit goes to 0. Okay. Now we are interested in the second derivative. Okay. So let me write the second derivative. fxy at 0, 0 is equal to limit delta y goes to 0 of fx 0 delta y minus fx 0, 0 divided by delta y. Okay, so here fx 0 delta y will be calculated from here. Okay, and the other one will be calculated from there. So this thing turns out to be minus 1. Okay, I'm skipping the details now. And if you calculate fy x 0, 0, you will calculate limit delta x goes to 0, fy delta x 0 minus fy 0, 0 divided by delta x. Okay. So this one again, you'll take the derivative. So this time I'm taking derivative respect to y. Okay, so you take the derivative respect to y of this thing, okay, and there put y equals 0, delta x equals delta x, and fy 0, 0 we found is 0. So this thing becomes, well, so let me make this thing, this part is actually delta y goes to 0 of minus delta y to the power 5 over delta y to the power 5, so equals minus 1, and this thing is limit delta x goes to 0, delta x5 over delta x5 equals 1. Okay. So you see that this is what you get for these things. Okay. And if you calculate fxy, okay, so you check that these functions, if you calculate, just write fxy at a point xy different than 0, 0, okay, so at this point you will see that, and fyx xy, okay, it's just taking second derivatives. I'm checking, so I have all these things here, okay, so they are not continuous at 0, okay, but fxy equals fyx at every other point naturally. Okay, if you take the derivative of this with respect to x first and then y first, you will get exactly the same expression as if you took the derivatives the other way around. What happens is that when you take the limits at the origin, you'll get these things will be different. Okay. Okay, so the function will not have, where is this function? So this function should not have a limit at the origin. So that's what the problem is. Okay, so let me do that part. That's also a crucial part of this. So maybe I can erase this part. Okay, so the aim of this exercise was this. So why did we get fxy 0, 0 different than fyx 0, 0? Okay, so consider fxy equal to, so at any other point yx, so this is when xy different than 0, 0. Okay, so if you calculate this at any other point, we have just one expression. So we are claiming that this function is not continuous at the origin. It doesn't have a limit at the origin. And as a consequence, the partial derivatives, these mixed partial derivatives, even they exist at the origin, they are not the same. Okay, so this function, I'll write this whole thing here, x to the 6 plus 9 I hope this is correct because I calculated this on Maple. Okay. Now restrict this to the path y equals lambda x. Okay, so that's the first thing that comes to mind. If it doesn't work, then you try other paths. The simplest thing is restrict this to a straight line with slope lambda. If the limit depends on lambda, this is not continuous at the origin. So when you simplify this, the Maple told me that the answer is 1 plus 9 t squared minus 9 t to the 4 minus t6 divided by 1 plus t squared cube. Okay, so this second derivative is constant along this line. It always takes this number along the line. On a different line, sorry, it takes the same number. Okay, so the limit of this thing as x goes to 0. Okay, so well, I wrote t here you cannot easily write lambda to maple. You have to type out lambda. So I write lambda here and tell maple that I'm using t. Okay, so the limit of this, so let's give this a name. So let's give this constant that depends on t. Okay, so limit of f x y as x y goes to 0, 0, but restricted to the path. Okay, so I'm using t, tx is equal to ct. Okay, depends on t. So the limit does not exist. That is, hence, f x y is not continuous at the origin. Okay, so if they are not continuous at the origin, then we do not it is not guaranteed that just because they are not continuous, their partial derivative is not the same. We do not expect that the mixed partials will be the same. Okay, and in fact, we calculated that one of them is +1, the other one is -1. Okay, so the partial derivative, the mixed partial derivative at the origin is not the limit of this at the origin. Okay, so that's one of the mistakes we do when we are doing calculations. Okay, such things hold in one-dimensional case again. Okay, so you can prove, I think, that if the limit of tangents, you take the derivative of a function, and if it has a limit at a point, then at that point the derivative of the function is equal to that number. I think we can prove such things. It holds in one-dimensional case. But here you see that I have this function, mixed partials. F of xy is defined. Okay, that's this one. Whichever way you calculate it is this thing. Its limit at the origin does not exist, but the values of these at the origin separately exist, and in fact they are different. Okay, so this is just an exercise to say that you have to develop a different intuition when you are working with the partial derivatives, with the several variables. It's a totally new world. So, okay, I get this thing. So let me do a few other things out of the way so that we don't come back to these things again. So another thing is implicit differentiation. So let me do an example on implicit differentiation. Okay. Okay, so we have time to do this at our leisure. Okay. So implicit differentiation. So let's do this on an example, because there are several things whose theory is too complicated to tell because there are lots of cases, but in real life only one of these cases hold, and let's do it on one of those cases. So z is a function of x and y defined by the equation. So I just invented an expression like this. I'm trying to make this so that x and y are not symmetric in this. Yz is equal to 99. Okay. So assume, okay, so we have to assume these things, but there's a way to check these anyway. So let's say z is differentiable with respect to x and y. Find the derivative of z with respect to x at a point. Okay, so now you see that this is a cubic equation of z. So if you stand at a point on the xy plane and you look up, you have a surface that goes some way, then comes back, and then it goes again. You will see 3 layers. Typically, you will see 3 layers of this surface. So it's not a graph anymore. Okay. So it's complicated. It's just like the simplest case is consider the equation of a circle. You stand somewhere inside the circle. On the x-axis, you look up, you see an arm of the circle, you look down, there is another arm. It's a quadratic equation, so at any point, the curve passes your horizon twice. So it's the similar thing here, but in one higher dimension. So here, it's not enough to say that we are calculating this at a point when x is equal to something and y is equal to something else. You should also tell which slope you are interested in on which of these layers. Okay, so that's why you have to give 3 points. So here, generally the notation is this. We say that we are doing this at this point. Okay, so there are three pieces of the surface passing on me, but one of them has the z coordinate 3. I'll calculate this at that point. Okay, so the rest is easy. You just do. Now, this is the usual implicit differentiation that we do with 2 variables. Now, differentiate both parts of the equation. Keeping in mind, okay, with respect to x, keeping in mind that derivative of x with respect to x is 1, derivative y with respect to x is 0, and derivative z with respect to x is your unknown. Okay, so this is your function. Okay, let's call it zx. Okay, so we want to find this. Okay, so with these things, so the derivative of this thing is 3x squared. Derivative of this, just to demonstrate it on an example, I'll put 0 here. This is a constant. Plus, this is chain rule here now. This is 6z squared times zx plus 6y is a constant. So this is 6yzx equals, on this part of the equation, I just put a number. So derivative of that is 0, but we can have other expressions here. You'll do the same thing, 0. Okay, now put x, y, z equals 1, 2, 3 to find. So let me see what I found here. Why didn't I calculate this? Okay, let's calculate this here before we go. Then I'll give you an assignment to find. Okay, so this is what we find here. This is 3 plus 3 squared is 9. 6 times 9 is what? Everyone is sleeping? I write 72. Okay, what do I write here? Z is 3, 6 times z squared. Nobody wants to risk his life because it is captured. Your answer will be there forever. Okay, I'll tell that these engineers don't know how to multiply if they don't have their smartphones. Okay, you can use your smartphone. It's allowed. What 54? Somebody came out this number without smartphone, so he's a smart guy. Plus, what is 6 times y? 12. Plus 12 zx equals 0. Okay, so what is zx now? Zx is equal to minus 3 over 66. Okay, so that's equal to minus 1 over 11. No, minus 1 over 33. So we didn't get the correct answer here. This is, if I divide this by 3, I'll get minus 1 over 22. Okay, so yes. So before we go, just 1 minute, I want you to calculate these numbers for the next time. So next time, I want these numbers here and we'll talk about them. So we have, you see that when this is given, it is not God-given that z is a function of x and y. Obviously, we can decide to live in the yz plane. We look towards the x-axis, then x is a function of y and z. Okay, so I have my things here, and I want to take their derivative with respect to x or with respect to y or with respect to z. Okay, so we have this this table. Okay, so evaluate at the point x, y, z equals 1, 2, 3. Okay, so what we found here it is 1 over 22. Okay, so, and obviously these parts are 1, so let me do 1/3 of your homework for you. Okay, so I want you to calculate these numbers here, and then next time on Monday we'll talk about it. Okay, thank you.